out of the idea of the four subspaces, the four fundamental subspaces, which are, of course, known long before my name for them. But
can you go through them? Can you go through the four
sure,
subspaces?
I can. Yeah. So the first one to understand is, so the matrix is, maybe I should say the matrix.
What is the matrix?
What's a matrix? Well, so we have like a rectangle of numbers. So it's got n columns, got a bunch of columns, and also got m rows, let's say. And the relation between, so of course the columns and the rows, it's the same numbers. So there's got to be connections there, but they're not simple. The columns might be longer than the rows, and they're all different. The numbers are mixed up. First space to think about is take the columns. So those are vectors. Those are points in n dimensions.
What's a vector?
So a physicist would imagine a vector, or might imagine a vector as an arrow, in space, or the point it ends at in space. For me, it's a column of numbers.
You often think of, this is very interesting in terms of linear algebra, in terms of a vector. You think a little bit more abstract than how it's very commonly used, perhaps.
Yeah.
You think this arbitrary space, multidimensional space.
Yeah, right away I'm in high dimensions and in the
dreamland.
Yeah, that's right. In the lecture, I try to. So if you think of two vectors in 10 dimensions, I'll do this in class, and I'll readily admit that I have no good image in my mind of a vector, of an arrow in 10-dimensional space, but whatever. You can add one bunch of 10 numbers to another bunch of 10 numbers. So you can add a vector to a vector, and you can multiply a vector by 3. And that's, if you know how to do those, you've got linear algebra.
10 dimensions.
Yeah.
There's this beautiful thing about math. If we look at string theory and all these theories, which are really fundamentally derived through math, but are very difficult to visualize. And how do you think about the things like a 10-dimensional vector that we can't really visualize?
Yeah.
Do you and yet math reveals some beauty underlying
great beauty.
our world in that weird thing we can't visualize. How do you think about that difference?
Well, probably I'm not a very geometric person, so I'm probably thinking in 3 dimensions. And the beauty of linear algebra is that it goes on to 10 dimensions with no problem. I mean, that if you're just seeing what happens if you add 2 vectors in 3D, then you can add them in 10D. You're just adding the 10 components. So I can't say that I have a picture, but yet I try to push the class to think of a flat surface in 10 dimensions. So a plane in 10 dimensions. And so that's one of the spaces. Take all the columns of the matrix, take all their combinations. So much of this column, so much of this one. Then if you put all those together, you get some kind of a flat surface that I call a vector space of vectors. And my imagination is just seeing like a piece of paper in 3D. But anyway, so that's one of the spaces. That's space number 1, the column space of the matrix. And then there's the row space, which is, as I said, different, but came from the same numbers. So we got the column space, all combinations of the columns. And then we got the row space, all combinations of the rows. So those words are easy for me to say, and I can't really draw them on a blackboard, but I try with my thick chalk. Everybody likes that railroad chalk, and me too. I wouldn't use anything else now.
Yeah.
And then the other 2 spaces are perpendicular to those. So like if you have a plane in 3D, just a plane is just a flat surface in 3D, then perpendicular to that plane would be a line. So that would be the null space. So we've got a column space, a row space, and there are 2 perpendicular spaces. So those four fit together in a beautiful picture of a matrix. Yeah. It's sort of a fundamental. It's not a difficult idea. It comes pretty early in 1806, and it's basic.
So playing